Welcome to the GEOTOP-A seminar. Today's speaker is Allison Moore, who will tell us about entanglement and invariance of theta curves. Take it away, Allison.
Thank you very much for having me. I'm delighted to be here. Before I talk about various things, let me take a moment and introduce some of my collaborators. I'm going to be talking about a variety of different projects with different groups of people. A lot of what I'm going to talk about is joint with Ken Baker, Dorothy Buck, Danielle O'Donnell, and Scott Taylor. And I'm also going to later talk about projects with two of my students, Matthew Elpers and Rayan Ibrahim from BCU. And I will probably briefly mention some older projects that were joint with Ty Lidman and Mariel Vasquez. And if I have time at the end, I'd like to also talk about another older project with Slaven Jabuka and Bebe Liu. So tons of collaborators and tons of things to say. And let me also point out that there are a lot of graphics in the background. And so some of the beautiful figures were made using the software NotPlot by Rob Sharayan. So what is it that I want to discuss? Well, I want to mention knots, links, and spatial graphs. This is a talk primarily about theta curves, which are a type of spatial graph, but it's it's an extension of knots and knot theory, and address why I care about this, particularly if you're interested in applications. Just a few brief comments about that. And then I want to get on to knotting operations in knots, links, spatial graphs, tangles, and other knotted objects, and then discuss the result that on knotting number one, theta curves are prime, which is a generalization of the statement that on knotting number one, knots are prime, a classic result from knot theory due to Charlemagne. After that, I'm going to talk about how we extend some knot invariants to theta curves, discuss some new bounds on a knotting number coming from some of these extension of invariants to theta curves. And then if I have time at the end, a little bonus content on the Gordian graph. All right. So a knot is, of course, an embedding of the circle into some three manifold, usually S3, but sometimes a different three manifold. And a link is a union of knots. Usually when we see pictures like what's on the slide, we're looking at a knot diagram, and that's a projection of the knot to the plane where we've indicated the over and under crossings. Spatial graphs, like knots and links, are going to be knotted objects in a three-dimensional space taken up to ambient isotopy, except now we're embedding graphs. So you have an underlying abstract graph, and then that gives you some sort of one complex that you embed in the three sphere typically. And the three images that I have on this slide are theta curves. So this is the particular spatial graph that I'm most interested in today, which consists of two vertices, three edges. There's another graph that has two vertices and three edges, which is the handcuff graph, but I'm going to mainly be talking about the embeddings of the theta curve. I'll mention lots of different knot invariants in this talk, but some of my favorite knot invariants are going to make appearances. So all knot invariants are, of course, assignments of some mathematical object to a knot, such that if you go and evaluate that object or that quantity, and you see that they're the same for K1 and K2, that implies that K1 had to be. I think I've left out I've made a little typo in this thing, so ignore that. But let me just mention my my favorite invariants. The unknotting number, the determinant, the signature. So these are all going to be integer valued invariants. The Alexander polynomial, which is a Laurent polynomial with integer coefficients. And then sometimes we need to use a covering space associated to the knot. So cyclic branched covers, and then calculate the invariance of those topological spaces. And that could be the singular homology or something more fancy like the floor homology. And I have an example over here, the trefoil, just to give a peek at some of these invariants. So for the trefoil, the unknotting number is 1. The determinant is 3, and the signature is -2. One of the things that we always see with knots of the single component is that the determinant will be an odd integer and the signature will be even. The Alexander polynomial in this case is a small polynomial. And the branch double cover, I'll say more about this later, is a lens space, L31. And then, as we do more and more things, we need more and more complicated invariants. If we want to go and write down the singular homology of the branched double cover, which I haven't really described, it ends up being Z mod 3Z. And then if we go and calculate an even fancier homology group, we see something that at least has 3 summons. Okay. So there are many, many, many different types of knot invariants. This is a screenshot of knot info. And so there's a lot of different invariants that I can't or won't be able to extend to theta curves, but we'll focus on just a couple of them. Okay, so why is it that one might care about knots or want to study knots, particularly if you're not already a low dimensional topologist or a geometer of some sort? If you are a mathematician, then, it's not a question that really needs an answer because knot theory is connected to geometry, topology, analysis, algebra, mathematical physics, combinatorics, everything that we like. But what about outside of mathematics? And I was really struck by the following quote, which I read about in the article DNA Topology, Experiments and Analysis, written by Professor Sumners. And the quote here is by E.E. David, Jr., and it's that knot theory demonstrates the seemingly inevitable utility of mathematics conceived symbolically without reference to the real world. So I love this quote, and I also am equally inspired by the image on the right of the slide, which probably many other people that have worked in DNA topology have also been inspired by. And the image is that of the chromosome of E. coli that's been extruded on the slide of an electron microscope due to Kavanaugh in the 70s. So it was shown back in the 1950s and the 1960s using autoradiography and electron microscopy that E. coli and other bacteria have long circular molecules of DNA. And in the case of E. coli, it's about 4.6 million base pairs packaged into a really tiny space. So it's an enormous challenge to try and describe, quantify, classify, and predict the kinds of complex entanglement in the cell. And because of this, we're generally motivated to develop rigorous tools and mathematical techniques that can be applied to study entanglement in the cell, or really any kind of natural entanglement. So that's just broad motivation. And in this, for the most part, I'm not going to discuss a whole lot about biology, mainly because I want to convey some results in knot theory and about spatial graphs. But I want to point out there's been a number of talks in this GEOTOP seminar devoted to applications of topology to molecular biology. And I also noticed that earlier this semester that Isabel Darcy spoke on DNA topology and natural knotting phenomena. So I could point people to those talks as well. So in this next slide, there's 2 images from the early 90s and the 80s of knots that were observed in experiments. So the image on the left shows a T213 torus knot that came out of an experiment in which a site-specific recombinase, which is a type of enzyme, mediated a reaction and produced this knot in a plasmid of E. coli. And in the image on the right, it's a different type of enzyme that's acting, T4 topoisomerase, a type 2 topoisomerase. And then also the trefoil knot was identified out of this experiment. So the enzymes that acted on these plasmids behaved differently, and we use different types of knot theoretic operations to describe those actions. In the case of a site-specific recombinase, it's what's called a band surgery. The 2 pieces of DNA are cut and they're rearranged. I'll have a picture of that operation on the next slide. In the case of the type 2 topoisomerase, it's essentially a crossing change. So let's say a little more about these unknotting operations, the basic ones anyway. So whether you're dealing with a knot, a link, or a spatial graph as the kind of underlying structure modeling your biopolymers or some other kind of chain, then there's different types of operations, simple operations you can do. One of the most basic is a crossing change, and in a diagram, we would just replace a positive crossing with a negative crossing. The other two most basic operations are the smoothings that you see here. So these go by a lot of different names. Sometimes they're called band surgeries, resolutions, H2 moves, or smoothings of a crossing. And there's two ways to smooth a crossing. You can smooth it horizontally and you can smooth it vertically. In the case of the vertical smoothing, when it's oriented as shown here, there's a naturally induced orientation on the smoothing. But in the case of this horizontal smoothing, there's no way to coherently orient the product. So in the image on the right, there's an example of what happens if we apply these to the figure 8 knot. And in particular, if we take the crossing in the lower left part of the figure 8 knot diagram and apply a crossing change, then we see that it yields an unknot. If we, instead of doing a crossing change, do one of these two bandings, then we get either a trefoil knot or a Hopf link. One of them's a knot, one of them's a link. And so these different types of knots and links result from doing these simple operations. When you have an unknotting operation, then you can ask about the unknotting number relative to that unknotting operation. Usually when people talk about unknotting number, they're talking about crossing changes. And unknotting number is difficult to determine. It's easy to define and very intuitive, but it's difficult to determine. It's a well-studied problem, and there's no way I could even begin to give a complete oral survey of what's been done. And many different obstructions exist to being either unknotting number 1 or to bounding the unknotting distance or crossing change distance between pairs of knots. There are obstructions that come from classical invariants, like the homology of the branch double cover. There's invariants that come from newer theories, like knot homology theories, like the Oshvath and Szabo-Tau invariant or Rasmussen's S invariant, or the torsion order of knot homology theories. In this slide, there's a picture, and this picture is the knot 10-8. This figure is from the PhD thesis of Eric Sterin, who was a colleague of mine when I was in grad school. And the example itself is due independently to Bleiler and Nakanishi, and it's a 10 crossing knot. But the issue is that this knot admits a 14 crossing diagram that has a knotting number 3. The 10 crossing knot, but if you go to a much bigger diagram, then it's a knotting number 3. But all minimal crossing diagrams have a knotting number 4. So it's not the case that you can even for such a small knot, 10 crossings isn't that much, but even in the case of 10-8, you cannot see sort of an optimal set of crossing changes in a minimal crossing diagram. So it's very subtle. There are a lot of open problems about unknotting number as well. One open problem is just to complete the determination of a knotting number amongst 10 crossing knots, and then 11, 12, 13 crossings. So even amongst small crossing knots, there's a lot of unknown. It's unknown what the unknotting number really is. Another open problem is to show that the unknotting number is additive under connected sum. So towards the second open problem, there's a classic result due to Charlemagne in 1985. And that's that unknotting number 1 knots are prime. So here is a figure 8 knot and a trefoil knot connect some together. Okay, the figure 8 knot is unknotting number 1, and the trefoil knot is unknotting number 1. Well, at least in this case, we know that the unknotting number cannot be 1, or this connected sum. So we would like to have a result that is similar to Charlemagne's result on unknotting number 1 knots and their primality. So we're going to pose this question about spatial graphs, and in particular about the theta curve. So let me first mention how we should think about the unknotting number of a spatial graph. There's a few things that we need to sort out first. So as we saw with the pictures before, we're going to take a spatial embedding of a graph, but we really ought to specify that our graph be abstractly a planar graph, because then we can really be clear what we mean for it to be unknotted. So The embedding of the planar spatial graph is unknotted if it can be isotoped to lie on the sphere. If we don't have a planar graph, we clearly cannot isotope it to lie on the sphere without some sort of extra crossings. And so we won't really have a natural definition of an unknot in this case. And when it is abstractly planar, it's old results of Mason and Tutt that tell us we do have this unique unknot in S3. So if we're in that setting, then we can say that the unknotting number is the minimal number of crossing changes required to make an unknotting, in a direct analogy to how things work for knots. Now, it's not the only issue to worry about. We also have different types of connected sum. So let's focus on the case of trivalent graphs. And we have two different connect sum operations to consider. There's an order 2 connected sum and there's an order 3 connected sum. So by this I mean edge connected sum, how we normally think of connected sums, and then vertex sums. And there's a picture of each one of those connected sums here. All right. Notice that if you have a more complicated graph and you say take a graph that's not trivalent, then, or that doesn't have even the same degree at a vertex, then you'll have some issues with this. Okay, now let's take a look at what happens when we connect sum together using the vertex sum, a handcuff graph and a theta graph. The handcuff graph is the other graph that has 3 edges and 2 vertices. Okay. The theta graph pictured on the left clearly has a knotting number 1. You can just change a crossing in the class. And the handcuff graph pictured on the right also has a knotting number 1. You can similarly change a crossing in the class that is sort of pictured on the left part of this diagram. However, if you vertex sum them together, then the same crossing change from the handcuff graph will also unknot the connected sum. And so we have that the unknotting number of this composite is now 1 and it's subadditive. So we have to be careful if we're using handcuff graphs. Our solution right now immediately is just to not use handcuff graphs. We're just going to use theta curves. And we can generalize Charlemagne's theorem. Unknotting number 1 theta curves are prime. So that is the statement. And by prime, we just need to be a little bit careful because we have the 2 types of connected sum. So really the statement is that if you're unknotting number 1, if you have an unknotting number 1 theta curve, then either theta is prime with respect to both the order 2 and order 3 connected sums, or there's a caveat, you could have the trivial theta curve, that's the unknotted theta, connected sum with any unknotting number 1 knot. And that is the picture that I have on the lower right. Just some unknotting number 1 knot that's been connected, order 2 connected sum to any edge. So that is the generalizing statement. We can say something even more though. So instead of just looking at crossing changes, we can look at a fancier type of a knotting operation. We're not going to use band surgery for this statement, but we can use something called a rational tangle replacement. So rational tangles are a type, it's a 2-string tangle where you've used a rational number to be prescriptive about how you will build this tangle. And there's a 1-to-1 correspondence between such tangles and the rational numbers. And they go in a kind of horizontal, vertical, horizontal pattern like what's seen here. So by doing a rational tangle replacement, that means you're going to be replacing a rational tangle by any other rational tangle of the same connectivity. So you could take a very big rational tangle and then replace it with a horizontal, a vertical, or a singly crossed tangle depending on its connectivity. If we allow for this more general kind of operation, then we get a completely analogous statement. Just replace a knotting number with proper rational tangle replacement unknotting number, and then we get the same statement. Okay. So studying theta curves really means studying 2-string tangles. We can observe just in a picture really that if you take the complement of a neighborhood of an edge, that's a ball, then what you're left with is two arcs properly embedded in the remaining ball, and so that's a two-string tangle. So there's a kind of trade-off. You can study theta curves or you can study tangles. It's two takes on the same thing. So in the course of proving our generalization of Charleman's result, there's a key proposition that we need to work out, which is a sort of tangle-ish version of the previous theorems. And that's that if T is a marked tangle sum of tangles and neither is integral, then T admits no crossing change to an integral tangle. By tangle sum, I mean T1 plus T2 is pictured here. By marked tangle sum, I mean we've fixed the endpoints of the arcs, and by an integral tangle, I mean one in which you can put in any number of horizontal twists but not vertical twisting. So just horizontal twisting, giving you an entangle where n is an integer. So the proof then of this proposition and then of the corresponding theorems for theta curves has a lot of working parts, but there is a special role for the tangle rho that you see pictured here in pink. So this tangle rho is not a rational tangle. It is also not a tangle sum. So rho contains no essential Conway sphere. It contains no essential torus or essential annulus. And it has other special properties as well. The numerator closure of this tangle is the unknot, which is, if you look at the picture for a minute, you can kind of convince yourself is true. The denominator closure of this tangle is the knot 10, 139. I'm not sure that you could visually convince yourself of this, but it is true. And why does that matter? Because the knot 10, 139 has pretty high a knotting number. It's 4. It also is sufficiently complicated to have pretty high proper rational tangle replacement on knotting number. We don't know that it's 2, but it's at least greater than or equal to 2. And that's a recent result due to Iltgen, Lewerk, and Marino. Okay, so what do we do with this special tangle rho? Well, let's suppose for a contradiction that our tangle sum does somehow admit a crossing change along an arc alpha, that's the crossing arc, to an integral tangle. Well, what we're going to do is we're going to add on this tangle rho to our tangle sum. So we add on the tangle rho, and then we take the numerator closure. In doing so, we produce a knot, which we'll call K rho. So if we do the crossing change along crossing arc alpha, that turns T1 plus T2 into an integral tangle, which up to some reparameterization, we can just assume is the horizontal tangle. And so this numerator closure just reduces to the numerator closure of rho. But rho had this very special property that the numerator closure was a knot. And by construction, rho plus the tangle sum T1 plus T2 is the sum of essential tangles, because rho is essential and T1 plus T2 is essential. Okay. And now what we're left with is this knot K rho, which is an unknotting number 1 knot with an essential Conway sphere. So these are knots that have been studied before. And in particular, we can apply work of Gordon-Luecke and of Eudave-Munoz. So by applying Gordon and Luecke's work, we have a kind of case analysis for how we can approach K rho. And what they proved is there's basically 3 cases. We either have that the crossing arc of interest is disjoint from all the essential summing spheres and tori in the exterior of K rho, or K rho takes on a special form. It is what is called an Eudave-Munoz knot, and it arises out of a particular has a particular structure, or it can be written as the union of 2 tangles, an essential tangle and then an Eudave-Munoz tangle. And so within these 3 cases, there's still a lot more work to do, but the idea is that we work towards a contradiction, or we work to move into a different case where there is a contradiction. And therein, we use this special tangle rho again. So it shows up again in case 1. After making some arguments, we arrive at the conclusion that if we take the denominator closure of rho, the unknotting number should be equal to 1. But that's a contradiction because this tangle was chosen for its special properties, and in particular that its denominator closure had a knotting number of 4. So that's sort of the idea of how this gets proved. At this point, I'm going to take a pause with this pretty figure that came out of NotPlot in case there are any questions.
Yeah, listen, I've got a question. Can you do any of this stuff for theta curves with more than 3 arcs? Like 4 of them?
That is a great question. I think that some of these things we may be able to generalize to theta n. We kind of found it. I think it's kind of the tangle problem's kind of hard because now you've got a 2n tangle. So our results don't immediately generalize, but I think something could be done. Thank you for the question. Okay, I am going to feel free to interrupt me at any time if anyone does have a question. I'm going to kind of switch directions a little bit and talk more about invariants. So a popular topic, really for no matter what kind of knot theory you're doing is how your preferred knot invariant behaves under unknotting operations, crossing changes, band surgeries, rational tangle replacements, or any other unknotting operation that you're interested in. So let's compare a couple of families of knots. If we take the T2 2n plus 1 torus knots, these are knots that are very popular in DNA topology. They occur naturally, and so they're worthy of extra attention for that reason and many other reasons. Well, as we increase n, the determinant goes up linearly. And same thing with signature. The signature goes down linearly, as long as you subscribe to the slogan that positive knots have negative signature. Then, and this is an easy thing that you can check just by hand using the Gordon-Litherland form or a Seifert matrix or lots of other techniques. So determinant and signature behave pretty well with respect to crossing changes, bandings. Signature in particular behaves very well under crossing changes and oriented bandings. So it's a classic theorem of Murasugi from the 60s that says if you have a pair of knots related by a crossing change, the absolute value of the difference of their signatures is at most 2. And likewise, if you have a pair of links related by an orientable band surgery, then the difference of their signatures is an absolute value is at most 1. But the determinant does not behave very well if we're looking at it from this perspective, if we're trying to bound it. So take, for example, the twist knots. The twist knots have determinant 2n plus 1, also another easy check. But any twist knot is related by 1 crossing change to the unknot. Okay. And then even fewer invariants behave well if you want to consider non-orientable banding operations. So earlier in the talk, we saw that there were 2 ways to smooth a crossing. In one way, there was an inherited orientation on the product, and in the other way, there was no coherent choice of orientation. These arise when you're talking about modeling, say, site-specific recombination at sites that are in direct repeat or inverted repeats. This is where this type of difference comes up. And it can be difficult to describe what is happening for non-orientable banding operations. And many knot invariants behave unpredictably under this type of operation. One thing that with my collaborator Mario Vasquez, we were able to prove a few years ago is that if you have a pair of alternating knots and you put some constraints on them, so you can ask for them to be alternating or perhaps quasi-alternating, and if you ask that they share the same square-free determinant, then you can bound the difference in their signatures when they're related by non-orientable band surgery. And their difference in signature is 8 or 0. So it's not as broad of a statement, but it is something that you can at least show. There are some constraints that you can put on it. So this is just one instance of a result about how an invariant behaves under a banding And there's a lot of other results in this general area that I don't have time to talk about. Some notable, other notable like exceptions are statements about lower bounds on crossing change and non-orientable banding distance that come from torsion orders in floor homology and in Kavanagh homology. And there's a lot of newer results about that that I'll just mention in passing. So just a couple remarks about the proof strategy that goes into these types of things. The theorem stating this difference in signature, the difference in signature being 8 or 0, is a corollary of a more general result about 3 manifolds that's based on techniques that we developed with Ty Lidman. And the idea is that the band surgeries that we're studying lift to integral Dane surgery in the branch double cover. And then the knot invariants that we're interested in, the determinant and the signature and the property of being alternating, correspond with properties about those branch double covers. The determinant is replaced with a statement about the first homology of the branch double cover. The signature gets replaced with the Haggard floor homology D invariant. And the property of being an alternating knot corresponds with the property of being in L space. So what we really go about proving is a statement about the behavior of the floor homology D invariants when we do integral surgery in an L space. We prove something there using the vast array of tools for Haggard floor homology, and then as a consequence, we get this statement about banding for at least some kinds of knots downstairs. A brief foray into this problem and this strategy, but then I want to get back to spatial graphs. So this is just a cartoon of the strategy of how that result came about. Generally motivated by recombination in DNA, and so we pose some sort of question about band surgery in knots, trying to determine when a pair of knots are related by a non-orientable band surgery. And to answer that question, we have to lift everything up into 3 manifolds and 4 manifold cobordisms between them, taking the place of our knots and our unknotting operations. Okay, back to spatial graphs though. So we want to do the same thing. We want to ask, what is the behavior of spatial graph invariants under unknotting operations? But before even getting to that, sometimes we have to concern ourselves with extending the definition of the invariant to the spatial graph in the first place before we can investigate that invariant's behavior under unknotting operations. So the next thing I want to tell you about is a recent project with 2 students where we extended the definition of the determinant to theta curves. All right, so here's a picture of a theta curve. It is simply a trefoil knot with an extra edge added to it, and I claim that the determinant is 3. Well, why is the determinant of this theta curve equal to 3? Well, the determinant of theta is the product of the determinant of the constituent knots. And so for this simple example, with my theta curve that I have pictured here, there are 3 constituent knots, meaning of the 3 edges in this theta curve, I take them pairwise and I get 3 knots, which I'll call K12, K13, and K23. And then this is an unknot and an unknot and a trefoil, so the determinants are 1, 1, and 3. Multiply them up and I get 3. Okay, that is that is not a definition, but rather the application of what we proved. So what we proved was that if you have a simple theta curve, then this formula that I just applied holds. So for a simple theta curve, the determinant of theta is the product of the determinant of the constituent knots. So let me, actually before going forward, let me point out what a simple theta curve is. The theta curve pictured here is simple because it contains at least one constituent knot that's an unknot. In fact, this one has 2. But a simple theta curve just means that at least one of those constituents is unknotted. And in the product formula, that means one of these determinants will be 1, and it could really be written as the product of the other 2. So It's good to mention how we want to think about determinant, or one of the ways that we want to think about the determinant for this theorem statement, because the determinant is a knot invariant that has many different instantiations. And we can calculate this determinant using Garrett's matrices. So this is Garrett's, the form of Garrett's, and or the Trotter form, and this is something that's about 100 years old. I think maybe a little less than 100 years old. What we can do is write with a knot diagram. We can find a checkerboard coloring, like what is pictured here in the image, a checkerboard coloring of the figure 8 knot. And when you want to calculate the determinant in this way, you define a matrix, and the entries of the matrix are going to be populated by taking the signed sum over adjacent shaded regions. So in the right side of this figure, there's a legend that tells me whether my positive or negative twist should be considered a +1 or a -1, what the sign is of this shaded surface. And that gives me the sign associated with each one of these crossings. And so what I'm going to do is sum these up, and that's going to be my entries off the diagonal. Along the diagonal of this matrix, I'm just going to make all the rows and columns sum to 0. That's what this second term does. And then what I can do is I have a matrix for which all rows and columns sum to 0. I guess it's column stochastic, I think is what it's called. And linear algebra tells me that I can delete any row and column, and I will then have an invertible matrix, and I can take its determinant. And that number in absolute value is how I can define the determinant of the knot. One way in which I can define the determinant of a knot. I can do this with the checkerboard shading of the diagram, or alternatively, I could use the take graph. So corresponding to the checkerboard shading, there's a take graph and actually a dual take graph, which is what's in the center of this image. For that, each shaded region gets a vertex, and then you place an edge between two vertices whenever there's a crossing connecting those two regions. The signs of the edges are the signs of the crossings. If you use the shaded regions, you get the take graph. If you use the unshaded regions, you get the dual of the take graph. And these are planar graphs, so they have well-defined duals. Okay, and I have this carried out on this slide here for this example of the figure 8 knot. Using that exact procedure, we can write down this matrix. For example, between region 1 and region 3, there are two crossings, and each of them have a plus sign. So in the entry 3, 2 of the matrix, or 1, 3 of the matrix, then we see the 2 show up. And every row and column sums to 0, and from here we can see the determinant of the 2 by 2 matrix is 5, which is the determinant of the figure 8 knot. Okay, so this is how we want to calculate the determinant of theta, but what does the determinant of theta really mean? And from here, it helps to go back to knot theory. So the determinant of the knot is many different things. It is the Alexander polynomial evaluated at -1, the Jones polynomial evaluated at -1. It's the determinant of the Seifert matrix V plus V transpose. It is also the order of the first homology of the branch double cover. And with the exception of the Jones polynomial here, all of these are really about cyclic covering spaces, whether you use the infinite cyclic cover or the branch double cover. So we want to adapt the last item on the list, which is to say, for theta curves, we want to use the first homology of a branched covering space. The picture that I have here is not a picture of a branch double cover of a knot, because I don't really know how to draw that. It's a picture of a branch double cover of the cylinder over the disk, but it's supposed to be suggestive of branch covering spaces. I'm going to define it to be the order of the Klein cover of the complement of the Klein cover of S3 branched over the theta curve. So this is an analog of the branch double cover of S3 branched over a knot, and you can actually do it iteratively with branch double covers. So if you have your theta curve, you can choose one of the constituent knots and then take the branch double cover of S3 branched over that knot. When you lift up to the branch double cover, the remaining edge there'll be 2 copies of it in the branch double cover, and they'll be identified at the vertices. So that edge, E3, lifts to edge 3 tilde, which is really a knot. And it is a knot on which the covering involution acts. So we can call that knot K, H, where H is the covering involution. Now you have a knot sitting in, well, if it's a simple theta curve, S3. If it's not simple, it's some other 3 manifold. But you can branch double cover that knot in that 3 manifold. And when you do it a second time, then you get to the client cover. So we are especially interested in simple theta curves. And so in that first iteration, we're branch double covering S3 branched over a knot. And so we get S3 again. That means that in the lift, the third edge is a strongly invertible knot. And so this means that there is an involution of the 3 sphere to itself. The fixed set of the involution intersects the knot in 2 points. And when we quotient by that involution, K mod the involution together with the axis forms the theta curve. And so there's this 1-to-1 correspondence between strongly invertible knots and simple theta curves. And the upshot for us is that then the determinant of theta is really the determinant of this strongly invertible knot. We can also observe that when we are calculating determinants for knots using, say, Garrett's matrices or Tate graphs, what we're really doing is a version of the matrix tree theorem. The matrix tree theorem says that the determinant of the graph Laplacian, which is the degree minus the adjacency matrix, is the number of spanning trees of the graph. And there's weighted versions of the matrix tree theorem as well. It's unclear who exactly to attribute the matrix tree theorem to. It's frequently Kirchhoff, but also Bott, Mayberry, Tutt. But in any event, this says that the tree weight is the determinant of the graph Laplacian, where now you're summing over spanning trees, but you can take the product over the edges of weights in each spanning tree. Now, the good news is that people working in graph theory are independently interested in studying spanning tree enumeration. And there's a group of authors, Chuku, Yan, and Zhang, who wrote down a product formula that said the number of spanning trees of a graph with an involution is in this product formula that you see on the slide. So it's the number of right graph for a certain way of breaking the graph into a left and right graph. It's not exactly a subgraph, it's more complicated than that. So basically in their product formula, one of the graphs, you take the induced graph on the left and center, and then you subdivide edges. And in the other graph, you take the subgraph induced by the left vertices, and then you add a sort of dummy vertex, and then you connect it up with a bunch of extra edges. So what we did really is we found that the 2 Tate graphs corresponding with the 2 constituent knots that weren't the unknot, but the other 2 constituent knots were precisely the same graphs that you would get from Chuku and Yan and Zhang's product formula. Well, not exactly on the nose. You have to change some edge weights around and double some edges to make sure that your edge weights still fall into the set +1 and -1. But modulo kind of rewriting the formula, we can apply it, and then when we put it all together, we get that the determinant of the theta can be obtained from this spanning tree enumeration formula. So that project was a lot of fun, and I'm going to take one more pause before I spend a few more minutes talking about more about unknotting operations.
Yeah, I've got a question, Allison. If you take an almost unknotted theta curve, that's one where all the constituent knots are trivial, then do all these invariants vanish?
Yes. So if you have unknot, then, oh wait, do we know that that's, hold on, let me be careful about saying yes so glibly. If we take the third edge and lift it Will we have are we guaranteed to have an unknot in the intermediary? Oh, I mean, I think that the Klein cover ought to be some sort of homology sphere, some sort of integer homology sphere, because the order of its homology will be 1. We will have the product of the determinants will be 1 times 1 times 1. So I think maybe we could have a non-trivial knot in the lift, but that's okay. I don't know if I answered your question.
Well, I've looked at almost unknotted theta curves, so they're a very interesting family. So
yeah, I think that the Klein cover will be an integer homology sphere.
I believe it.
Yeah. Okay. Well, one can ask, well, okay, can we also get bounds on a knotting number from thinking about these types of invariants, determinant, signature, these types of things? There's a classic bound. This is we need to start with the older bounds before we get to the newer, fancier bounds. There's a classic bound due to Murasugi, again, where the a knotting number is bounded below by the signature. And in fact, you can put down a 3-part inequality where you have the signature, the slice-Euler characteristic, and the unknotting number. And here, with the slice-Euler characteristic, I mean something like the smooth 4 genus. And it is convenient for us to write this bound instead in terms of the orbifold Euler characteristic. It's just a rewriting of this bound, but if we write it in the following way, 1/2 signature less than or equal to 1/2 the orbifold Euler characteristic is less than or equal to the unknotting number. That's the way we want to see it. Then work that's in progress. I don't want to say a ton about this because it is in progress. But something that we're aiming for is to show a similar statement for theta curves and for more general spatial graphs as well. We want to state something for more general trivalent spatial graphs that have a 3 coloring that are sort of like theta. But what it will reduce to in the case of theta curves is a statement that is similar. So 1/4 the signature of the theta less than or equal to 1/4 minus the orbifold Euler characteristic is less than or equal to a version of the unknotting number. So there's all kinds of details in this. Instead of just plain unknotting number, we need to count crossing changes that happen between same color edges and mixed color edges slightly differently relative to some 3 coloring that exists on this graph. And when we calculate this maximum orbifold Euler characteristic, we are no longer using Seifert surfaces, but we're using a generalization of this. We're using Klein foams properly embedded in the 4-ball. So there's definitely some details to work out. The good news is signature, a notion of signature has already been defined by Gilles and Robert for Klein graphs. All right, so just for a few minutes, I'm going to switch directions again. And since we're on this topic of unknotting operations, I want to mention another object that is fun to study, the Gordian graph. So you can organize knots or links or really any object that you're studying relative to the unknotting operation that you're interested in by organizing everything into a graph. So in the results that I will state, there are many different unknotting operations at play, but I'll pretty much focus on crossing changes and H2 moves. So what is the Gordian graph? It's a huge abstract graph. Every isotopy type of a knot is a vertex in this graph, and you put an edge between them if they're related by a crossing change. That's the standard Gordian graph. If you want to generalize this, just change out crossing change for H2 move or past class move or whatever operation you're interested in studying. That's a Gordian graph, or more generally just a knot graph. as opposed to spatial graph. So this is a very complicated graph. It is connected, that's good, but it is countably infinite with countably infinite degree at each vertex. And it's worse than that. At every vertex, there is at least a complete graph with infinitely many vertices. That's due to a result of Hirasawa Uchida for crossing changes, Zhang Yang for H2 moves, I believe. And the proof of this is basically a picture like what is drawn here. If you stare at this picture for a while, you can convince yourself that if you add an arbitrary number of tangles U to this picture, then you can create an edge amongst any of the knots created by adding extra tangles U. So this gives you your K infinity. So it's very hard to study such a complicated graph. So when you're in the business of studying infinite graphs, you might run across Gromov hyperbolicity. And basically a geodesic triangle is delta thin if each edge is contained in a closed delta neighborhood of the union of the remaining two. So think of your standard Euclidean triangle, that's not delta thin. And then a metric space is delta hyperbolic if every geodesic triangle is delta thin, or we just say Gromov hyperbolic if it's delta hyperbolic for some delta. All finite graphs are hyperbolic, so that's not very interesting, but an infinite graph could be hyperbolic or not hyperbolic. And there's lots of different reasons to care about hyperbolicity. It's important to hyperbolic geometry, the study of hyperbolic groups, combinatorial group theory. Assessing whether a metric space is hyperbolic in general can be reduced to assessing hyperbolicity in some associated graph due to a result of Bowditch. And there's applied reasons for being interested in hyperbolicity as well. But for what I'm going to say next, we're just motivated in studying the global structure of knot graphs. So Gambado and Geese established a quasi-isometric embedding of the integer lattice into the Gordian graph. That pretty much says that it is not going to be hyperbolic. This is for crossing changes. It's a quasi-isometric embedding, so it's quasi-injective, but it is not a quasi-isometry. There's no surjectivity statement there. We generalized their result, showing that the Gordian graph is not Gromov hyperbolic, and the HN Gordian graph for any HN move is not Gromov hyperbolic, and we used a different type of proof. Our proof strategy was to construct fat triangles, meaning that in whichever graph we're dealing with, for any delta, we need 3 knots to make a triangle. We need it to be a geodesic triangle, and then we need to show that one path, one edge, is not contained in a delta neighborhood of the other 2 geodesic paths. So for example, when we're dealing with the H2 Gordian graph, we use torus knots, T29 and T215, and connect sums of them to make our geodesic triangles. For other operations, we use different types of knots. So we get this big complicated triangle of knots, and the first task is to show that it is a geodesic triangle. That turns out to not be very hard. We can use invariants coming from the branch double cover to show that the paths are geodesic. The obvious unknotting operations using H2 moves at the top, bandings, show us that the distance from, say, K0 to K1 is less than or equal to M. To show the distance from K0 to K1 is greater than or equal to M, it's the number of generators of the homology of the branch double cover. The hard part comes in trying to show that the third edge is not contained in the delta neighborhood of the other 2. To do this, we need to identify some knots, say K3, along that third edge and bound the distance away. Can we do it with the existing strategy using branch double covers? No. Unfortunately, branch double covers didn't work. A priori, there could be some sort of shorter path, not necessarily through torus knots or connect sums of torus knots, but just through some other arbitrary knots that put K3 close to edge L1 or L2. In order to make it work, we have to change how we're getting our bounds. So to do that, we change the degree of the cover, we change the coefficient ring of the homology group. And that's part of the reason why we needed to use T215 and T29, so that when we looked at other cyclic covers and we set about calculating the homology of those covers, which turn out to be some Brieskorn manifolds, then we are able to achieve these bounds. And then when we change from H2 moves to crossing changes or HN moves, sometimes we have to change the way that we're forming the triangles using different knots, use completely different knot invariants, like knot from covering spaces, or in some cases, change the cover again, because there's many cases to do. All right, and so I will stop right there, and thank you all for your attention. And I have some references here for the figures and the biology results. And a shout out to Knotplot, which has been so great for making images of knots.
Well, Allison, thank you for a terrific talk. The floor is open for questions. At the end of your talk, you had some non-delta thin triangles, and you were using Brieskorn manifolds or something. You were changing all sorts of cyclic covering spaces.
Yeah, we change the cover. Like, we have these T2 connect sums of T215 and connect sums of T29, and we want to get some sort of lower bounds. So I believe we're using results of, I'll have to look in the paper to get the citation, but there are some existing bounds that say if you take the number of generators of like an M-fold cyclic branch cover, then this is going to give you a bound when you're looking at HM moves. So when we study like HM moves, we need to use different cyclic covers. And so we choose classes of knots to form these triangles where we can identify what the cyclic cover is, and then have some sort of means of calculating its homology, not directly, but by using facts about Brieskorn manifolds, cyclic fiber spaces, stuff like that.
Very interesting. How about some other questions? Okay, well, let's thank our speaker for a great talk.